All right, we're going to play with the WHAS 500 data today. There's two WHAS data sets. They both come from the same experiment. They're just two different data sets from it. We saw the WAS 100 last time, so I'm getting WAS 500 this time. Data and script. Okay. So what we're going to do with these data, excuse me, is consider building a model. An explanatory model. So we've talked about differences between explanatory and predictive models, and in the context of explanatory modeling, where I want to fit a model that explains some relationship of interest, and typically that means you want a p-value or a confidence interval for one or more relationships. We have to be careful when we're doing this model building exercise for the reasons that we saw in the simulation that I had earlier. If you do overly aggressive model selection where you just ask the data, where you rely completely on the data for choosing the model, you can get these overfitting issues and increased error rates. So your p-values can mean not what you think. Your confidence intervals cannot have the coverage probability that you think. Having said that, in the context of, say, survival data, it's not as easy to informally investigate the relationships between variables and decide which covariates are important and which ones aren't, to decide functional form. Is it fair to assume a linear relationship between this covariate and the response? So this book Applied Survival Analysis had, I thought, a good breakdown of how to build a model, how to decide on which covariates to put in the model, what transformations, if any, to do of the variables, any interactions to include in the model. So let's talk through these data and consider building a model with them. These come from a heart attack study where we have 500 individuals and 22 variables. Got something in my throat. So the main goal was to describe factors that are associated with trends over time in incidence and survival rates following admission for a heart attack, hospital admission for a heart attack. So these are all people who were admitted for heart attack, and we have, among other things, time of follow-up, which is event time, and a censoring indicator for that. But we do have a bunch of interesting covariates like BMI, history of cardiovascular disease. Some of these are numerical, some of them are categorical. Over at the right, it summarizes types of variables. So, you work for the data team, and you just collected the data. You have your new 500 observations, and it's up to you to decide what model to use in explaining and in investigating these data. You have 22 covariates. So one possibility would be to include all the covariates in the model. Somebody thought that these covariates were important enough to collect them, so maybe we should go ahead and just include them all in the model. If you include all the covariates in the model, you also need to consider, well, do we need interactions between any of these variables? And if so, which ones do we need interactions for? Do I need two-way interactions or three-way interactions or even more? If a variable, if one of these covariates is not relevant to the problem, if it does not contribute information, or if it's not the variable of interest, like a treatment variable or BMI, if we wanted to look at specifically the role, the association between BMI and survival. If it's not a variable like that, then arguably we should not include it in the model. There's no need to add a variable to the model if it's not playing any substantial role. Having said that, some variables belong arguably in the model, even if they don't have a demonstrable impact with these data. Something like age or gender arguably should be in most any bio-related model, just for interpretability purposes, if nothing else. Nobody's going to believe that the model that we have is appropriate for the population if we haven't adjusted and incorporated for, very core basic demographic differences. So in particular, even if you have a model that you're considering and say age and gender don't have really small p-values, you might be tempted to look for, to pursue a so-called parsimonious model and say, well, if it doesn't have a small p-value, it's not important, so I'm just going to remove it from the model. So in what follows, we will do a little bit of that, considering should this variable be included in the model or not. But I want to just kind of generally argue for be willing to include variables in the model independent of whether they are statistically significant in the model when they have domain, real domain meaning. Age and gender arguably belong in the model. Some of these others maybe not. Okay, so I have read in the data, I think. Yep. Let's look at summary. I don't see any missing values. LOS, what is this variable? Length of stay in the hospital, I guess. Length of hospital stay. So LOS is number of days from hospital admission to hospital discharge. And the mean and the median are about 5. But there is one person who was in the hospital for 47 days. So that's a potential outlier. We might want to look at that a little more closely. In fact, let's look at a histogram. So right skewed, which you would expect, you can't have negative length of stay. Most of the stays are less than 20 days, but there are a few extreme ones, and that 147 is the most extreme, off by itself. Okay, what else do we have? These variables are all binary. So the mean is actually proportion. Proportion of our subjects who had AFB, which is atrial fibrillation. Proportion who had SHO, CHF. Some of these are very rare. What else do we have? Systolic blood pressure, diastolic blood pressure. This is pretty big relative to the others. Let's look at a histogram of diastolic blood pressure. Doesn't look so bad in the picture form. So 198, I'm not that worried about that. Doesn't look like it's different enough to be called an outlier to me. Okay, I don't really see anything else all that worrisome. So let's start thinking about building a model. How would you begin choosing the model? At the end of the day, we want a model. It's going to be a survival analysis regression model. For us, that means Cox proportional hazards model. So we're going to have this model that says log hazard equals linear model. Not beta 0, but beta 1 times covariate 1 plus beta 2 times covariate 2 plus possibly interactions. So who goes in the model? Step 1 to asking that question would be to look at each variable individually. If we were doing usual linear regression, like a continuous response variable and a continuous predictor variable, say, we could draw a scatter plot and just look at it. Does it look like there's a linear relationship between x and y? If not, then arguably that variable doesn't need to be in the model. If it was a categorical variable, what we could do is make maybe side-by-side box plots of the response for each level of the categorical variable. And in that case, if all the boxes are right next to each other, again, it doesn't look like that's an important variable. So in the survival case, it's a little bit harder to make pictures because we don't just have a continuous response variable. Now we have this event time and survival probability that goes with it. What we can do is for the categorical variables like gender, CVD, cardiovascular disease, AFB, atrial fibrillation, and so on, for each of these, one of our tools for working with survival data is fit a survival curve. And if we fit survival curves to different levels of a categorical variable, we can use the log rank test to test whether the survival curves are different. So if the survival curves are different by gender, then that's indicative of the hazards are going to be different for gender. So if I do a log rank test comparing survival to the levels of gender, and we see evidence that survival does differ by gender, then that's evidence in favor of including gender in the Cox model. So let's do this first. Let's do a log rank test comparing survival curves by gender. I'm really not a fan of using p-values to make choices with respect to building a model. But like I said, it's a little bit harder with survival data to not look at p-values because I can't just make a scatter plot easily. I can't make side-by-side box plots easily. This log rank test is an assessment of differences. I would just say don't place too much attention or weight on p-values. The more you use formal model selection techniques, more you use the data to decide on the model, the better or the worse you are in terms of chances of making mistakes. But certainly, a small p-value in the log rank test suggests that there is a difference in survival curves by gender. So we do have evidence that gender belongs in the model. We could also make the pictures of the survival curves. I'm not going to do that. I'm just going to kind of go roughly through the variables and decide yes or no. Does it look like there's a substantial relationship between gender and survival time? If so, we'll go ahead and include it in the model. If not, even if this p-value was big, going back to what I was saying earlier, I would argue for gender belonging in the model anyway. People who do clinical trials, for example, gender and age and race, they are going to be in the model. They need to be in the model for interpretability reasons, if nothing else. So, long story short, we're going to keep gender. It's going to go in our model. Next to the servdiff command, I have a tabulation command. So table up fstat with gender. What is this doing? It is tabulating censoring and uncensoring by gender. The issue is if there's too few events in one of the levels of gender or any of our variables, then we can have trouble fitting the model. If you try to estimate a regression coefficient for a Cox model, a log hazard ratio, comparing gender 1 to gender 0, if there were no events in gender 1, then it won't be able to estimate that. So I'm going to make this table for each of these categorical variables just to keep track of do we have sufficient numbers of actual events in each level. In this case, we do. For gender 0, we have 111 deaths, and for gender 1, we have 104 deaths. So I don't see any problems with gender, and I do think gender belongs in the model. Let's look at CVD. Also a small p-value, relatively small p-value, suggesting that there is an association between CVD and survival time. And we'll look at this one. Table. Reasonable number of events in each category of CVD. So if we continued through this, all of these except for, I think, this one, complete heart block. Which one is that? Complete heart block is AV3. So all of them except that one look like there's an association, like they belong in the model. They seem to have an association with survival time. AV3, let's look at it. So it had not a very small p-value. So we might consider AV3, maybe it does not need to be in the model. If we also look at the tabulation of it, AV3 is interesting because it's a very rare event. Only 11 people out of our 500 had total heart blockage. It's probably because you die pretty quickly if you have it. So there's very few events with which to estimate a beta coefficient for AV3. That may be enough reason for us to leave it out. Unless it's of specific interest, this may be more trouble than it's worth if we were to add it into the model. It doesn't look like it explains much, and the model might struggle to come up with an estimate, converge at an estimate with too few events in at least one of the categories. So we're going to put a question mark on that one. And also cardiogenic shock, which is SHO, has a similar issue. It has few events in one of its categories. So this was also a rare event. Only 22 people had this event. How about the log rank test? What did it look like for this variable? So it had a very small p-value, but it has pretty small numbers of events, or at least pretty small numbers of show equal 1. So I recall from trying to fit this model in previous semesters that adding these covariates that have so few levels of 1 created computational issues with fitting the model. So I'm going to remove these from consideration. AV3, there's really no reason not to. Doesn't look like it explains much, and there's really not any information about it, period. SHO maybe is a little more controversial, removing it, but I'm pretty sure we will have computational issues if we don't. So I'm going to initially include all the variables that we just considered, all those categorical variables, except the two that we described, AV3 and SHO. So that's categorical variables. We're building up a model. Which covariates belong in the model? We've considered the categorical variables. Now let's consider the continuous variables. We have age, heart rate, systolic and diastolic blood pressure, and BMI. In terms of assessing the association between a continuous variable and survival time, again, it's not easy to just draw a scatter plot like it would be with a normal response variable. So I'm going to again use an inferential tool to guide the decision of whether these variables are important. Specifically, let's do each variable one at a time in a Cox model. So I wouldn't do surv-diff, because that's for log rank test, comparing survival curves by categories. I don't have categories now, I have a continuous covariate. So what we could do is Cox proportional hazards model relating survival time to each individually. And then we can look at the results of that model to ask, does this look like a substantial explanatory variable? The 95% confidence interval on the hazard ratio for age, for every 1 unit increase in age, we estimate a hazard ratio of 1.07 with a 95% confidence interval of 1.06 up to 1.08. So that does not include 1. We knew that because the p-value was small, but that's indicative. That's telling us there is evidence that age plays an explanatory role in survival. Age also is one of the variables that you would arguably always want in a bio model, at least when dealing with humans. So I'm pretty comfy with including age. How about heart rate? Another tiny p-value. Confidence interval goes from 1.01 up to 1.021, which is not not a very big effect. 1/100th of a unit, a 1% increase in hazard, essentially, on the lower end. But apparently it was enough. The Z statistic, the Wald statistic, estimate divided by standard error, is enormous. Well, not enormous, but it's quite big. That's because the standard error really was so small. The coefficient itself is relatively small, but the standard error is even smaller, so that wound up giving us statistical significance. So we have, again, evidence that heart rate is explanatory, even if the effect size is not all that large. If we continued through, we would see similar stories for all 5 of the numerical predictor variables. So let's plan on, at this point, including all of them. So we have several categorical variables and now 5 numerical variables. So let's consider our first multivariate model as the one that includes those that we just chose. Here is Cox proportional hazards with age, heart rate, systolic blood pressure, diastolic BMI, and gender, CVD, and the other categorical variables that we picked. Let's look at this. All we've done so far is consider each variable individually, but now we've put them all together. And we know enough about what regression is doing to know that a variable that looked very explanatory, very predictive individually won't necessarily look important when other variables have been included. For example, systolic blood pressure. When we looked at systolic blood pressure alone, it had a small p-value. There's a statistically significant linear association between systolic blood pressure and log hazard when considered alone. But this coefficient is linear association between log hazard and systolic blood pressure, holding everything else constant. So among people with the same age, same heart rate, same diastolic, and everything else, holding all those constant, if you increase systolic blood pressure by 1 unit, this is the estimated log hazard ratio. And it's not anywhere near statistically significant. That can happen in a variety of ways. If one of the other variables is correlated with this one, then it could be that the other variable is getting the statistical significance, and this one is not giving us any additional information. So it doesn't actually show up as important. Okay, so what do you do at this stage? You have this model, and not everything is statistically significant anymore. That one's got a big p-value, CVD does, AFB does, and these last 2 do. One option would be to just get out or take out all the variables that don't have small p-values. I would argue against that, at least as a blanket move or a default move. I don't think you should think in terms of let's throw out anything that doesn't have a small p-value. You can lose interpretability in the model, and as we'll see in just a second, you can, even with a non-statistically significant contribution, you can wind up allowing confounding by not including a variable. So even if it's not statistically significant, it can affect the interpretation and the estimates of other variables, making the model less appropriate. So here's what the book that I referenced recommends. We're going to start back at that multivariate model, the first one that we considered, and consider might we be able to remove one or more of the covariates? The way we're going to do this is certainly the variables that are the first candidates for removal are ones that do have big p-values. That's where we would start, at least, is variables that have big p-values. They don't appear to be important once everything else is in the model. But the way we're going to assess it is to remove a variable and look at the coefficients of everything else before and after removal. If the coefficient for a variable changes depending on whether another one is included, then that's evidence, or at least, potential evidence of confounding. So confounding is when you can't tell the difference between an effect that's due to this variable and an effect that's due to that variable. You can't disentangle them. It could be either one. What's that? Multicollinearity is slightly different. That's where we have multiple variables that are highly correlated with each other. It's not exactly the same as confounding. I'll do a little lecture on confounding at some point because I think it's something that we want to be comfy with. One indicator of confounding is if you take the confounding variable out of the model, other coefficients change. What that means is that variable is important to elucidating real effects of the other variables. The effects of the other variables are hidden or masked if the variable is not included. So what you want to be aware of and guard against is if you pull a variable out of the model and the coefficients for the others change substantially, then you shouldn't have pulled that variable out. If a variable has a big p-value and when you pull it out it doesn't do anything to the other coefficients, then that's about as clear a case as you can hope for go ahead and remove that variable. So for example, here is the model where we're going to remove systolic blood pressure. Actually, I'm going to remove two at a time, which probably isn't the best idea. But we had two covariates that had p-values bigger than 0.9, systolic blood pressure, and a categorical variable, history of cardiovascular disease. Let's consider removing both of them. And our question will then be, did the other coefficients change much? So fit coefficient was the original multivariate model that had everything in it. And fit 1 is the model that took out those two covariates. So we could look at these coefficients, age and age, roughly the same, 0.049 or so. Heart rate and heart rate, roughly the same. Diastolic blood pressure, minus 0.01. BMI, roughly the same. Gender, roughly the same. AFB, roughly the same. CHF, myocardial infarction, and MI type. They all look roughly the same. So I'm comfortable at that point, those variables are gone. After we do that, we could reassess. So I'm going to accept fit 1 as the updated model. Let's look at the new model.
All right, so if you remove it and the coefficient changes, so what you should do is probably just to keep this in even if it has a high p-value, right?
Yes.
So you can consider the interaction between these
So the question was, if the coefficients change depending on whether or not this one is included, does that mean anything about an interaction? We'll consider interactions in a minute, but not necessarily. A confounding is not the same thing as interaction. Interaction would say that the effect, like the effect of one variable, depends on the level of another variable. What confounding is doing is that the estimate of the effect depends on whether or not this other variable is included. You can actually get an incorrect estimate. So one simple example of confounding, kind of a classical example, is suppose we have people who are recent A&M graduates, and they either got a degree in science or the arts. Let's change it to engineering or the arts. And each graduate can be characterized as either male or female. So, it is possible to create some data such that the average, and the data that we're going to have is salary, average salary. So what's the average salary of males who graduated with engineering, females who graduated with engineering, and so on? It's possible to have data where the average salary of males is substantially bigger than that of females. When in fact, the real relationship is opposite. So it is possible to have marginally the estimated effect of gender is that males get more. But if you went and looked within the same category, you could have data where female is greater than male. And within arts, that female is greater than male. So that in a regression kind of setting, failing to adjust for degree type would give you wrong estimates of gender effect. That's confounding. When without account for degree type, so like unadjusted for degree type, we have one picture. Males make more than females. But if you include degree type in the model, if you adjust for it, you have the opposite pattern. That's an extreme illustration of confounding, when the estimate is different depending on whether the covariate is included. Certainly, if you have that type of thing in your data, you want to include the variable that we're considering adjusting for or not adjusting for. Okay, so we fit our new model, and we might reconsider again. What's that? I thought I fixed it. Did I not do that? Nope. Okay, so here's our updated model. And we might look again at considering removing variables. AFB has a reasonably large p-value. Myocardial or MI order has a even bigger one. Right, so now the largest p-values correspond to MI order and MI type. 0.75 and 0.36. I don't know why I didn't include AFB. I should probably include that. But I'll just follow my code. Let's consider removing these two, MI order and MI type. When I remove them, the coefficients did not change again. Not very much at least. 0.05 versus 0.049, 0.011 versus 0.010. That's not bad. That's not bad. That's not bad. A little bit different. And CHF, just a little bit different. So I'm comfy with removing those as well. After doing that, now we have this model. There's one coefficient that has a big p-value, so let's consider it. After doing this, the coefficients barely change. So let's go ahead and get rid of that one. And now we're left with this model. And I mentioned in the script that gender is kind of marginal in terms of statistical significance. But again, gender is one of those variables that arguably should always be included. So I don't particularly care in this case. For interpretability reasons, let's leave gender in the model. And any of those other variables that we dropped, if there was special reason that they needed to be in the model, if doctors don't consider your case as a heart attack patient without consideration of this particular variable, then that should be in the model too. Okay, so we're comfy at this stage with a handful of variables that we've chosen to put in the model. Other things that we should consider, anytime you have a model, you need to consider the assumptions of that model. And do they look appropriate? Do they look reasonable? If they don't, then you have no business trusting the results of the model. So what we're going to do, the continuous covariates, currently we have them in the model as if there's a linear relationship between them and the response. When we did linear regression, we would take the residuals. So if we fit a regression model like yi equals beta 0 plus beta 1 xi, x is continuous, y is continuous. One thing that we did in order to diagnose the model is we computed the residuals. And we drew a picture of the residuals versus the covariate. And we were asking of this picture, is there any evidence of non-flatness? If, for example, there was a U shape to this picture, that would suggest that's not an adequate representation of the relationship between x and y. X is not really linear, or y is not really linear in x if there's a curved relationship like that. Any kind of systematic deviation from the horizontal zero line is indicative of we didn't get the functional form right. So we're going to try to do something similar here. Again, it's a little bit harder because I can't make pictures like this as easily. But here's what we're going to do. This was recommended by the authors in that book. We can, if I want to ask, does it look like there is a linear pattern between a covariate and log hazard, one way we could do it is to break the continuous covariate into categories. So bin it into low values, middle upper values, and high values. And we could estimate coefficients for each range. So we could fit a Cox model to age categories, for example. Age is a continuous covariate. We're interested in, does age have a linear relationship with log hazard? The way we're going to try to assess it is categorize age. So this right here is going to turn age into a factor instead of numeric. We now have these categories. Age is either from 30 to 59, or from 59 to 72, or 72 to 82, 82 to 104. So if I fit this model, Cox proportional hazards, this is a factor. So instead of treating age like a linear covariate, we're going to treat it like a categorical variable. So let me show you the output of this. Now we have a log hazard ratio for the middle category, log hazard ratio for the upper mid, and log hazard ratio for the upper. If age is linear in its effect on log hazard, then at least approximately these should be linearly related to the locations of these intervals. For example, we could take the midpoints of these intervals, plot them on the horizontal axis, and these estimated coefficients on the y-axis, vertical axis. And if that looks roughly linear, then that's evidence that age is roughly linear for this model. So what I'm going to do here is, these are the midpoints of the intervals that we just defined. And I'm going to plot the coefficients that correspond to each of them. The question is, does it look roughly linear? So that looks roughly linear. As far as I'm concerned, I'm comfy with assuming that age is linearly related to log hazard. If we did that for the other continuous covariates, heart rate looked fine, diastolic blood pressure looks fine, body mass index looked fine. So we didn't seem to have any problems with the, quote, functional form of these continuous or numerical covariates. What we'll do next time is consider interactions. Do I need any interactions? Which ones do I need? Talk about that. And then the other big issue with Cox proportional hazards is the assumption of proportional hazards. And that is an assumption that is made with respect to every covariate in the model. So we would need to assess, does it look like there is proportional hazards with respect to age? Yes or no? Does it look like there's proportional hazards with respect to gender? Yes or no? And so on. There is a function that does that in one fell swoop for us, so we'll use that. Making pictures to check that is a little harder. I will show you an example of how to use a picture to assess this. But in this example, we'll just use cox.zph. So in your homework, I'm asking you to do this kind of process for the two data sets in the survival package. Which covariates do you include? Consider one by one. Then put them all together into an initial tentative multivariate model. Consider removing any of the variables that can be. check on the functional form of the numerical variables. Does linearity look right, or do you need something like a quadratic or something? Consider interactions and consider proportional hazards. Okay. Any questions? All right. See you Monday. Have a good weekend.